Hey, Katie.
Hi, Ben.
I discovered something recently. The New York Times has been kind of killing it with their recipe game.
Oh, yeah, I really like the New York Times cooking site. It's got lots of tasty food that's good for winter.
Yeah, apparently one of the soups was so good that it became referred to on the internet as hashtag the soup.
Oh, that's intriguing.
And you should try it. You all should try it. Everyone that can hear the sound of my voice should try the soup because it's really good.
Is this related at all to our topic of discussion today?
Not at all. No.
Okay.
It's just something that was on my mind. Let's talk about the technical implementations of implementing privacy protections.
That has nothing to do with soup. Nothing at all. Yeah, sounds great.
You're listening to hashtag linear digressions. Okay, so today we are actually talking about GDPR.
GDPR. So the people who are working in industry, probably a lot of you have heard of this and are groaning right now. Those of you who are still in training, perhaps, or in academia, this might not be something that you have to think about that much. But as soon as you get out into the industrial world, if you ever make it out into the industrial world, for sure, especially if you work with person data, you have to think about this.
Right. These are privacy protections. So, I mean, one of the important parts of GDPR is person should be able to say, "Hey, company X, do you have any data on me?" And furthermore, if you have any data on me, I'd like that to be deleted, please.
Yeah, and so GDPR is a set of regulations, basically, that the EU passed a while ago and that went into effect somewhat more recently, in the last year or two, into full effect. And they attach to those privacy requirements a lot of pretty stringent fines that they can apply to companies that are operating in the EU or that deal with data on EU citizens if those companies aren't adhering to the tenets of GDPR, which, as you say, mostly have to do with things like if a company has your data, they have to give you information about what they use it for. You have to have a chance to be able to withdraw your data from their data set. There's many, many articles of this that everyone is kind of trying to figure out how to reconcile.
Right.
And so if you're a data scientist who wants to do any kind of data analysis on people, so say you're trying to build customer acquisition model, you're going to build that on top of person data, like customer data, and depending on where that data comes from and what people have consented into and out of and all of these kinds of things, GDPR has now introduced a lot of technical overhead that you should at the very least be cognizant of and maybe should be a big part of your workflow these days.
Right. One of the interesting things about this law is it's not just, hey, company X, do you have a user account for me? Like, that would actually be much simpler because companies are used to looking up user data based on the user ID or something like that. But this is actually much more broad than that. This could include logging. You know, did someone... was someone logged in and visited a website, and then that website, just for debugging purposes or something like that, logged some information about the user. Just like, oh, the user's username is this, or their email is this, or whatever. It can be really difficult not just to go through all of these different places that you might be storing user data, either intentionally or unintentionally, but furthermore, to know, do I even have this user, any data on this user? Because it could be hiding in a lot of different places, or your databases could be, tremendously sized.
Totally. And so that brings us to the first topic of technical discussion here today. So we're going to talk about a couple things that are totally different sides of the planet, but that have to do with actually implementing this stuff in GDPR. So the first one will be probabilistic data structures and Bloom filters, which have all kinds of uses beyond this, but is one of the ways that you can speed up that lookup time by a whole heck of a lot.
What does probabilistic data structures mean?
Great question. So are you familiar with, say, the dictionary data structure in like Python?
Not in Python, but yeah, it's the idea that you can have a bunch of stuff and that stuff. For example, if you have a list, that's a bunch of stuff in a particular order. You have a first item, a second item, a third item. A dictionary data structure is a little bit different. They're not ordered, but instead they have keys that you can look them up. So, for example, you might, in an actual dictionary, which is kind of where it gets the name from, in an actual dictionary, you can look up the definition of a word by going to that word in the dictionary. And there's a very easy way to find that word in the dictionary. In this case, it's alphabetically sorted, but a computer might be doing other things in the background. So it's a way of getting to the thing that you have a name reference to very, very quickly, rather than having to go through the entire thing looking for your piece of data.
Yeah, exactly. So one thing that's worth noting about dictionaries in this context is that if I'm looking for something that's in a dictionary, what I do is I put in the key of the dictionary, say like, hey, do you have a value that corresponds to this key? And when the dictionary will either return to me that value, or it will throw a key error or give me some other kind of message that says this isn't in the dictionary. And with 100% certainty, if it returns something to me, that means that that thing was in the dictionary and it has now been returned to me. There's zero ambiguity or uncertainty about that. And likewise, if it says it's not in the dictionary, then I know it's not in the dictionary. And so it's very deterministic, if you like. Probabilistic means that it might give it back to me, or it might not under certain circumstances. And while that might not sound particularly reassuring, the idea is that probabilistic data structures allow you to sometimes do things much faster than you could do with a deterministic data structure.
Okay, why?
Great. Yeah. So let's talk about how a Bloom filter actually works. So Bloom filter, when a Bloom filter, we say it's a probabilistic data structure. What a Bloom filter will do is when you ask for an element in a Bloom filter, it will either say it's probably in here, or it will say it is definitely not in here. So it makes mistakes, but only one way. It never accidentally tells you something isn't there if it is. But if it says that it is in there, it only means that it's pretty likely to be in there. It's not certain.
Interesting. So it's not a deterministic or a probabilistic data structure. It is, for one answer, it's deterministic, and for the other, it's probabilistic.
Yeah. I mean, usually they just call them probabilistic data structures, but I think that's a good point. It's a little bit asymmetric.
Okay. And actually, that's interesting talking about it in the context of privacy, because the thing you care about in the context of privacy is, do you have data on this person?
Yeah, exactly.
If the answer is like probably, or it's possible we don't, like, it doesn't really matter as much if you make a mistake in that direction, but if you make a mistake in the other direction, that could be some hefty fines.
Right. So it's very expensive for you to mistakenly leave someone's data in your database if they've asked you to remove it and you've mistakenly told them that you don't have it, or you thought you deleted it, but you actually didn't, or whatever. That's an expensive mistake to make. But thinking that you have someone's data and then going through your logs to retrieve it, that might be annoying. It might be something that you certainly don't want to do at scale. You don't want to do that with everyone. But compared to like tens of thousands of dollars of fines for making a mistake the other way, it's like somewhat less of an issue. So Bloom filters...
Or millions, depending on the size of your company.
Yeah. So Bloom filters set you up pretty well for the constraints of the problem that you're trying to solve. So how does a Bloom filter work?
I was just going to ask you that question, because it seems like a hard problem to solve. I'm imagining, though, there's probably some really beautiful, simplistic solution here.
Yeah, it's pretty elegant and it's pretty understandable. So imagine, the key to a Bloom filter is thinking about hash functions. So a hash function is basically a function that takes some kind of input and deterministically creates some kind of output. And in this case, what it will take is some kind of entry that you want to see if it's in the Bloom filter, if it's in the data structure. So let's say that's your name, Ben Jaffe. Are you in this database? And the hash function will then map your name, Ben Jaffe, onto a string of ones and zeros. And that string of ones and zeros, it'll be deterministic, so it'll be mostly zeros, and then it'll be a few ones. And the length of that string is the size of the Bloom filter. So let's say that your Bloom filter is 1,000 elements long, and Ben Jaffe maps onto the, I don't know, let's make it comically simple. The first, second, and third bytes or bits of the Bloom filter get set to 1 for the entry Ben Jaffe, and all the rest of them are 0.
Okay, and just to make sure I'm understanding correctly, you've got this Bloom filter, and actually, because we're talking about binary, let's imagine that you've got 1,000 switches that are all next to each other, right?
Yep.
You're saying that if you put me into your database that this Bloom filter is backed by, then you're going to turn on switch 1, 2, and 3. If you put Katie Malone into the database, maybe it switches on switches 100, 249, and 600 or whatever. And you do that for every single user in your database, and you end up with a bunch of switches flipped on. Is that what you're saying?
Yeah, that's basically how it works.
Okay, but still a lot of them switched off.
Yeah, so there's a lot of artistry in basically how long is that output that it makes. Like, is it 1,000 long? Is it way, way longer? Is it 1 billion long? And then each time we hash something, how many bits get set from 0 to 1? Because, so if you're the only person who's in the database, you're the only entry, so it's all zeros except for elements 1, 2, and 3. Then if somebody comes along and is like, Ben Jaffe, are you in my database? Then they put your name into that hash function. It gives back the same 3 elements. They go check them. They're all set to 1. And they're like, Ben Jaffe could be in this database.
Oh, I see. So if Ben Jaffe's not in the database, then 1, 2, and 3 are not necessarily turned on. But it's possible that 1 or more other people happen to flip 1, 2, and 3 on. Maybe
Right.
a bunch of individuals, 3 individuals, each flip one of those bits. And so you might end up with this situation where Ben Jaffe is not in your database, but 1, 2, and 3 happen to be flipped on. And so you end up with this result of, like, we think Ben Jaffe is probably in the database, but it's possible he's not. And in this case, he's not.
Yep, exactly. So you just go in, you find the bits that are the hashed correspondence of the thing you want to look at. If any of them are set to 0, then you know that they're not in the database, because if they were in the database, they would have been set to 1. And if they're all set to 1, then that either means they're in the database, or, as you can tell, if you were to put enough things, if you were to overfill your Bloom filter, eventually all of your zeros would become 1s for, like, a good hash function. And then everything is going to return, yes, this is in, yes, this is in, yes, this is in. So that's where some of the artistry comes from, is you need to sort of tune all of this and try to figure out how big you think your database is going to be, and how much you're willing to put up with hash collisions. Because usually if you get a hash collision, you get one of those, we think that this person is in the database, then depending on the context, maybe you'll just assume that they're in the database, and that gives you a pretty good next thing to do. Maybe it means you do this more expensive, more complete scan, but you kick into some other type of process at that point.
Okay, so basically the false positive rate, which you're also talking about as a hash collision, is expensive in the sense that once you think that a user is probably in the database or might be in the database, you then go and do something, like maybe go to delete their data or find their data or something like that. But the more false positives you have, the more you have to do this more expensive operation. And so it's kind of a trade-off between how expensive is it to go and look someone up who's not in the database versus how expensive is it to have a larger Bloom filter.
Yep. So I think we've already kind of given some context about where this could be interesting for GDPR. Again, just like scanning through big data sets over and over and over again to try to figure out if you need to do point deletions. Easier if you have some of these things to help you out. The second application is very different, but no less interesting. So as warm up here, we're going to talk about machine learning algorithms and how they can maybe be trained to forget people who don't want to be part of the algorithm anymore. You and I have talked about this just a little bit, sort of parenthetically, a bit in the past. This was something you were wondering about. Want to recap that real quick?
Yeah, I guess the question is my data in the model itself? if my data was used to train the model. I mean, maybe you can't recover data about Ben Javi from a model that happened to have his data passed through it, but in some way, in some fashion, the model is the way it is, in part because of the data that the company has on me.
Right. So if we were to train a model yesterday, and you were in the data set yesterday, and then today you got in touch with us and said, please delete me, then we could delete you out of the database. But in general, unless we retrain the model, it'll retain some residual memory of the fact that you were there when it was trained. And, you know, arguably, this is the kind of thing that GDPR, the text of the law can be a little bit vague about, but people who really understand these things say, like, yeah, arguably that person hasn't been fully expunged from the records of this company if they're still sitting around in the model. And so the thing that I thought was kind of interesting, I was reading up a little bit more about this lately, and people are thinking about this. Are there algorithms that machine learning algorithms that can be amenable to forgetting their training points for exactly this use case? And found a pretty interesting little paper. We'll have a link to it on lineardigressions.com. There's also a couple other really good references about Bloom filters I'll toss up there for those of you who are curious. But this machine learning paper is talking about a few different algorithms, recognizable algorithms from machine learning that basically by introducing extra bookkeeping data structures as auxiliary infrastructure that you build when you build the model, then you can build a model that when you extract a person's data from one of those auxiliary data structures, effectively extracts it from the model and thereby allows you to forget people, which is pretty cool.
That is very cool. This is an area that's actually really interesting to me. A similar question is raised by, you were talking about hashing functions, right? Yeah. Where, and just to summarize a hashing function a bit more, you've got some data that goes into the hashing function, and you've got usually a smaller stream of bytes or bits that come out the other end. And generally speaking, hashing functions go one way. You can put data into the hashing function, get a hash, but you can't go backwards. You can't take a hash and necessarily get the original data, because you could actually have multiple different arrangements of data that would produce the same hash, even if it's probabilistically, if it's unlikely, but it's still possible. Typically, hash functions are considered to go one way unless you have, some data to test against or something. And so one question that I was raising actually with some coworkers recently is, does it count as user data if you take user data and put it through a hashing function? And now that hash is technically generated from their data, but you can't get to their actual data from the hash. It's kind of an interesting philosophical question of the law seems very cut and dry and black and white when you first read it, but the question of what is personal information is a really interesting and thorny one when you get into it.
Yeah, that is an interesting philosophical point. I don't know the answer. I confess I've never actually thought about that exact thing before. I can see how it's thorny. And I think a lot of data scientists are struggling with some of this stuff because the law can be tidy looking, but it's kind of vague. It tends to be. In some ways that's appropriate because you don't want legislators drafting technical specifications, and arguably if they did, it would just make them easy to get around. You kind of want to have this notion that there's the spirit of the law as well, and that it's flexible to the stuff we might invent in the future. But in the meantime, a bunch of very smart and thoughtful folks are also trying to think about how to reconcile this with all the machinery we already have. So how do you do stuff like database deletions and machine unlearning and stuff like that? And well, that's why we're here today, I guess.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.